Hi, class. Welcome to the next section, chapter 8.2 volumes. We're going to talk about how to use integrals to find volumes of solids. So let's go ahead and get started. Again, we can use integrals to find the volume of a solid. We know that an integral gives us the area under a curve in two dimensions, right? So if I have just x and y axis and I have a function, the integral will tell me what the area is under that curve from a to b or over the life of the curve. So if the integral gives us the area in two dimensions, how do we extend that into a three-dimensional object in order to find a volume? So there's actually a few ways to do it. In Calculus 3, you learn of several ways to do that. But for right now, what we're going to do is we're going to look at what our three-dimensional object would look like as a projection onto a two-dimensional plane. So what does that mean? Well, you see it all the time, right? Whenever you see a shadow on the ground, that is a projection of a three-dimensional figure onto a two-dimensional plane, right? So a projection, an easy way to think of a projection is as a shadow that is being cast down from a light source over a three-dimensional object. Okay. Um, Lucky for us, we don't have to think that far ahead. Okay. In Calculus 3, we do have to visualize things in three dimensions and what the projection in two dimensions would look like. But for now, all of those projections are going to be given to us in the form of a function, or I'm sorry, of a area that is bound by two or more functions. So this this projection is already going to be given to us, right? Very similar to what we saw in the last section, where we're given two curves and some sort of a boundary, and we need to integrate and find the area between those two functions. We're doing a very similar thing here, okay? We're just kind of adding an extra layer onto it. So our second step is that we need to figure out what's the best direction to integrate. Should I integrate in terms of x, or should I integrate in terms of y? As we saw in the last section, sometimes trying to force a function into x is not the best way to do things, and sometimes I should change my approach and I should look at things um, sort of through a rotated lens and try to think of things in terms of y instead. Okay, so again, we want to take a slice in either x or y, depending on which seems to be easier. And then what we're going to do is we're going to find the cross area of the slice that we took in three dimensions. Okay, so we're going to take our two-dimensional object, figure out which direction to integrate, x or y, and then think about what that would look like in three dimensions. And it should be a cross area, and then we'll take that cross area and integrate it across our bounds to give our three-dimensional object. Okay, there we go. And that's my fourth, is to integrate that function that gives us the cross area across our bounds, right? So let's look at our definition so we have a little bit formal manner of looking at this. Let's say that we have a solid. We will call that solid S. And let's say that solid lies between x equals a and x equals b. Okay. If the cross-sectional area of our solid lies in a plane, which we call P of x, which lies through the x-axis and perpendicular to it, we'll call that A of x. So this A of x gives us the area of a cross section at a point x within our solid. Um, Ideally, A is a continuous function. Then the volume is the integral of that area at whatever x, okay, across the entire bounds of our function, right? So that might be a little bit hard to swallow. Maybe you want to pause, rewind it back, and re-listen to that. So again, we're starting with this limit definition, right? Because we're taking our cross-sectional slices to get infinitesimally small and have an infinite number of them. So it is a continuous sort of object, and then we integrate across that. So let's go ahead and do an example. So let's find the volume of a I'm sorry. A frustum is a right circular cone, okay, that has a height of h and has a lower radius r and an upper radius little r. So think about a cone, like an ice cream cone that's been put on the ground, and you kind of just chop the pointy top off, okay, so that the lower and bottom part are parallel. So it'll look like this, okay? I took a cone, I kind of chopped the top off, and so the base and the top are parallel to each other. There's a height of h here, and the top has a radius little r, and the bottom has a radius large r. Okay, so if we project a slice of this onto an XY plane, it'll look like the following. In order to make this a little bit easier to look at and to integrate and to use, we're going to actually rotate the object and center it on the x-axis. Okay, so it'll look like this. So if I took a slice, let's say it's right down the middle, and I kind of turned it so that it was, nice and easy to work with, it would look like this. Okay, so it doesn't really matter how I turn it because the volume of the object is the volume of the object, right? So here makes it easy because obviously, if I take slices, it would be nice to go up and down. If I kind of centered it on the axis like it was right here, it would be hard to go up and down, and I'd have to go horizontal in order to take slices. So we're trying to keep this easy for us in the way that we work with things and keep it kind of normalized a little bit. So here we're going to go up and down when we take slices, right? So we will be taking our slices in the x direction. In order to do this, we need to find the function for the height. So again, this looks like a line, so this will give us a height, right? So I need to find the equation of this line. So if you look, there's 2 points here. There's little r on the x-axis, and there's this point h and big R. So I have 2 points, means I can find the equation of a line. In order to do this, we need to find the function for the height, which is the radius at any time. This height here is the radius. So at this value of x, the height here is the radius of the cone, right? So the line that connects them has the points 0r and h and big R. So again, h is the height. So if we subtract the y's, big R minus little r, h minus 0 just gives us an h. So that is the slope times x plus b. Our b in this case is the y-intercept is r. So this is a relatively easy function for us to find for the radius at any point along x. Okay, so again, just so that we're very clear, along any point in x, this function I just found, this equation of the line, is the radius. So at this point, if I go up, that's the radius, right? At the end, this is the radius. So, which is big R to little r. All right. So, the area of a cross section at any point is pi r squared. Well, our radius is given by a function, so that's whatever that value is at x squared. So pi r squared is the area of a cross section because a cross section, again, if we come here, if I took a slice here, okay, and I expand that into 3 dimensions, that is a circle, right? A slice would be the same as a circle cross section. So I replace my function Rx for the function I just found, that line that gives the radius. I have pi, this is Rx squared, okay? So again, I have my graph at any x, we'll call it x sub I. That distance here is the radius at this point. As you can see, this is a rectangle because that is my slice, it is infinitesimally small. So that cross section is a circle with radius, right? So here you can see that the sizes even match up. Okay, I'm trying to match everything up here. And so this radius at this point is given by r minus r over h, the value of x sub I, right, at that x value, plus little r, okay, just like here. So in order to integrate, okay, I would just integrate this area function, this cross-sectional area function. Again, the width here would be delta x, right? It's a very, very thin area. And as I take more and more and more slices, that cross-sectional width gets small. So I can set this up as an integral as The volume is from 0 to h, pi r squared. Again, delta x is uh, the width of this bar, which again we just call dx when I take the limit as n goes to infinity. Okay. So if I start to simplify this down, I can pull out the constant pi, right? If I expand this, I get the first term squared, the last term squared, and 2 times the middle term times the middle term. So 2 little r times this slope times x, right? So this is just an expansion, very, very standard. But again, look, now I have r minus r over h squared, so I can expand this even more, okay? Or I can keep it as is since it's just a constant term. It's unnecessary to have to do more. So my variable here is x. I'm integrating in terms of x. So this turns into a cube term, and when we drop that down, it turns into the 1/3 that we have here that you see. Okay. For this is the same thing. 2r, r minus r over h is a constant, and so this just turns into an x squared. I multiply it times 1/2, so this 2 should drop out. Okay, so we just have the pi from the beginning, and then our constant term here, r times r minus little r over h. I evaluate that at my bounds, h and 0, and then this turns into 1/3 times, I'm sorry, it's just r squared x, okay? And then our pi I bring in as well, and evaluate at my bounds from uh, h and 0. So notice all of these have x. So whenever it's just a constant times x, constant times some power of x, constant times x. So when I plug in 0 for this, it goes away. When I plug in 0, it goes away. When I plug in 0, it goes away. So all of these I just need to evaluate at the upper bounds of h. So I'm going to get this whole constant term h cubed, right? Minus nothing. Plus this whole thing h squared plus this whole thing h. Okay. So here I have I'm plugging this at h. Here I have my h as well. So again, you might be saying, why is this h? So remember, this is h squared, and I'm plugging in h cubed, so that cancels out to just an h. Okay. Here, same thing, h on bottom. Here, h squared. So h over h squared is again just an h. And then this will be as well pi r squared, and then just an h. So before I start doing crazy stuff like expanding this, let's go ahead and pull out common terms. Okay, so I have a pi uh, over 3h. So I'm going to bring in the 1/3. I'm going to pull out the h from all of these terms. Okay, so h is all the way on the end. Pi is all the way on the end. I'm leaving the 1/3 with the expansion of r, big R minus little r. Here, I'm leaving the little r times big R, little r times negative little r. And this is just r squared. So again, I factored out pi and h, and anything else I left on the inside, and I expanded this r minus little r squared. Okay. So now I can start to combine like terms inside of here. I need to distribute this 1/3 first, so we'll go ahead and do that and combine our like terms. So first off, I distribute this 1/3, so 1/3 r squared, 1/3 little r big R, 1/3 r squared, and then I combine those, right? So this is 2/3 little r big R plus 1 big R little r, so that's left with a positive 1/3. This same thing, this turns into, well, these two can cancel out, little negative r squared plus r squared. So then I just distribute this 1/3 times this r squared. Okay. And so from here, I'm going to pull out the only common term that I have, which is a positive 1/3. Okay. And on the inside, I'm left with r squared, little r squared, and then r times little r. And this cannot be factored. I cannot simplify any more than I have at this point. Okay. So let's go ahead and do one more example. All right, so we want to find the volume of the solid that is obtained by rotating the region enclosed by y equals x cubed, y equals 0, and x equals 1 about the line x equals 2. So this is much more complicated. So sketching a quick graph, we'll have the following. Okay, so we know what x cubed looks like. We know what these lines look like, and we can draw a dashed line where we want to rotate everything about, right? Our line of symmetry. So I have my number line here. Okay, I have y equals x cubed, right? I I'm going to put y equals 0, x equals 1, and y x equals 2. Okay, so y equals x cubed. Y equals 0 is just the x-axis. Okay, then I have x equals 1. So this is the area enclosed by the function, the straight line, and the axis. And then my line of rotation, right? My line of symmetry is at x equals 2. Right? So that's my intersection point. That's the area I'm interested in. And that is my rotation line, my line of symmetry. And so I kind of get this on the other side, right? I'm rotating about this line. So I kind of have this like line over here where it will show up again as a solid, right? So if I took a slice, I wouldn't want to slice up and down because I'm rotating this way. So I would want to take a slice parallel to the x-axis, right? So I'm going to be looking at this in terms of y. So really my integration should be terms of y. Okay. So we can see that when we rotate about the line x equals 2, a slice is going to be a ring, okay? The inner radius of the ring is 1. So if we come back to our picture, the distance between the line of symmetry and the edge is 1, right? So it's a radius of 1 here, radius of 1 here, the radius is 1 for any ring that I make. The inner radius is 1. The outer ring is defined by a function. It changes along the line y equals x cubed. Okay. So it'll be easier to look at it as a function of y. So we want to solve for x, right? We want to get x alone. So by doing this, we end up with 2 minus y to the 1 cubed. Now you might be saying, where the hell did this 2 come from? Well, we're looking at the radius, right? So the distance away from here. So I have 1 plus, and then whatever value I have, right? So you might say, okay, well, what about the 2? Well, my values here are centered about 2, right? So I have to say, I'm going to go up to 2 and then subtract from that whatever I need to subtract. Okay, so my value here is not a radius, it's a radius that comes from 2. So 2 minus, and then whatever this function value is what I need. Okay, so 2 minus this curve. And so if you're ever questioning it, why don't we just check, right? So we're going to look at this by looking at the lower bound and upper bound, right? So I'm going to take my function, my radius for the outer radius. And I know when x is 0, okay, or when y is 0, I should have the maximum radius, which is 2, right? So if I plug in y equals 0, I should have a radius of 2. When I plug in y equals 1, I should have a radius of 1. Okay, so let's just check that balance and make sure everything works out. And if you want to, you can check an intermediary. So if I went right to 1/2, right? So, and I said y is 1/2, it should be whatever would be there, right? But I feel like checking the bounds is good enough. Don't just check 1, you got to check 2. So again, let's check our bounds and see what happens. So if I plug in 0 here, I should get the max radius of 2. Okay, max radius of 2. Okay, which I do, right? When I plug in 0 here, 2 minus 0 is 2. When y equals 1, when I plug in 1, I get 2 minus 1, which is a radius of the outer ring of being 1. Okay, so I'm fairly confident that this uh, tells me my radius very well, right, for the outer radius. So if I want to find the area of a slice, I got to find the outer radius and subtract from that the inner radius, right? Because again, if we go back to our picture, it's a ring. So the outer radius minus the inner radius gives me the area inside of the ring. Okay, so bigger circle minus the inner circle. Okay, so area out minus area in. Remember, the area for a circle is pi r squared. Okay, pi radius out of the outer ring squared minus pi times the radius of the inner ring squared. So my outer ring has a function of 2 minus y to the cube. I'm sorry, 1/3 power, the cubed root, I should say. And for the inner radius, it's just a constant 1. Okay. So when I start to simplify, I get 2 minus y to the 1 cubed squared, which I squared. And I also subtract 1 from that. So at first I pulled out the pi, and then I just went ahead and expanded this, right? So 2 times 2 is 4, minus the 1 is why I have 3 here. Y to the 1 cubed squared makes it a positive, so I have y to the 2 cubed. Then you can multiply these two together and double it, so that's why I have minus 4 y to the 1 cubed. Okay, so this makes sense to me. I could try to factor it again from here if I want to, but it's not really necessary because this is the function that gives me the area of any ring at any slice. So I just need to integrate it. So no use trying to do more work to it. I'm going to integrate from 0 to 1 because we go from 0, y equals 0. This is the point of intersection. I don't have to go past that. Okay. So from 0 to 1 in terms of y. So the first term, this goes up by 1, so this turns into 5/3. Remember, we flip that, and that turns into the constant from 1 to 0. Again, notice when I plug in 0, it's just going to go to 0. Nice thing here, when I plug in 1, it just turns into 1. Okay, this thing is going to go up to, so plus 3 over 3 gives us 4/3. So I'm going to have 3 over 4 in front. And 3 over 4 times 4 will cancel this 4th, and I just have a 3, and the power is 4/3. And this turns into 3 to the y, also evaluated at 1 and 0. Since all of these have a y, the 0 term is negligible, and since the top term is 1, it just turns into 3 over 5 pi minus 3 pi plus 3. Okay, very nice. So I can just pull those out. So you can see I have a 1/5 left over from here. This, when I pull out the 3 and the pi, I have just a -1. And when I pull out the 3 and the pi here, I have just a +1. These two things cancel, and so my answer is 3 over 5 pi, or 3 pi over 5, however you want to talk about it. Okay, there you go. And that's how we do rotations. See you guys on the next video.